Alright, so here today we're going to do Lab 7. Momentum and impulse, or just impulse, I forget what, it doesn't matter. Alright, how do we measure impulse? Well, impulse is equal to force times time. Alright, so we just have to measure force and time. How do we do all that? Well, if you look here on this track here, I've got part of it set up over here. We have this here, a pulley clamp, and this here, short rod, and we're going to put a force probe on here. Obviously, we see a problem to start with. Do you see what the problem is, Elena?
It's not straight?
There's something in the way. We have to move it. So now we have to take into account that moving this thing, to move it properly, we have to do it like I said here. You see, you don't take the T-nut off, and then you slide it back underneath and tighten it up down there. See that? We didn't lose the T-nut. That's important. Right, Greg? All right. So then we put the force probe on here. Now this is the way I see most people put it on. They'll put it on like this. Okay? Looks fine. And it would almost work, except for one thing. It doesn't work. Well, it does work. But what happens is, with this much out here like this, it's going to vibrate a lot when the things hit it. That is bad. So what you want to do is you want to put it up here and lower the whole thing down. This will dramatically reduce the amount of vibration in your setup and make your data a lot better. Now you still have to go through and calibrate and zero the force probe like you normally would, but since I covered that in other videos, I'm not going to bother with it now. The one thing that's important here is you want to make sure that there's space underneath the force probe, between the force probe and the track. Now for the first couple ones of these, all you have to do is you take the cart and you push it along here. It's going to have a thread attached to it, and some of them the threads break and some of them the threads don't break. And what you do is you're going to get a force probe signal, if we hooked it up, but I'm not going to. And we're also going to get from all the way down at this end here, our motion detector is going to give us a signal. So we're going to have F delta T. We're also going to know the mass of the cart so we can get M delta V, and mass velocity. All right, and you can fill out the sheet. It's an easy sheet to fill out. All right, and you'll calculate the change in momentum with respect to the impulse, and you'll see if there is any. Okay. Now I'm trying to remember if there's anything else for this particular lab, and I don't think there is. I think it's pretty straightforward. If I remember something, I'll record another video. By the way, I just wanted to point out that Monica in the morning lab and Justine in the afternoon lab both have watched iCarly, and they don't want anybody to know, so don't tell anyone, all right? Okay, don't tell anybody at all. All right. I promised I wouldn't send out an email telling everybody that too, so I'm not going to. All right. So now, how do you get that F delta T? That's the impulse. Well, what it is if we look at, let's go over to the blackboard. I think we have a much better photographer today. Usually it's me. Okay, if we have, this is our force signal over time, and it goes up like this, our impulse would be the area under this curve. Now, you could spend a lot of time on Logger Pro getting each one of these data points and figuring out the area under it. That would be a complete waste of time. There is a symbol on the, just like with the stat and the linear fit and all those ones, there's another one that looks like something like this, and it's all colored in, meaning that it'll give you the area under the curve. Oh, that makes your life easy, doesn't it? Okay? I'm trying to think, because I always get confused between this lab and the next lab. So let me see if I got my lab book here. Yeah, here it is. Let's see if I forgot anything. Oh, it's all printed upside down. Damn it. All right. Impulse, impulse, impulse. Now the pre-lab's pretty easy because you just have to figure out the area under a triangle. If you can't figure that out, well, it's 1/2 base times the height. Okay, so we have the track, we have the string. Yeah, you really just have to do this like, yeah, 4 times. You have 4 different cases, I think, that's it. You do each one 3 times. Don't get too obsessed with, one set of data. Just take the data, take it fast, keep moving it along. Your percent differences in the first, oh yeah, there's a 5th one. Ooh. Yeah. Okay. Yeah. It's a good thing I found this too. So the first 4 parts are all just like we showed you on the track. Sometimes you have a thread, a strong thread. Sometimes you have a weak thread. So sometimes the thread breaks, sometimes it doesn't. And in the second 2, you have you take the hook off the probe and you put a rubber stopper on. Really easy. And now instead of pushing the force probe away, pushing the cart away from the force probe, you're pushing the cart toward the force probe. Okay? And that's especially where that vibration in the probe comes in handy. Now the 5th part is a little different. Okay? And in the 5th part, what we're going to do is we're going to use a very special device. It's so special, we only have 1 of them. Okay? It's called the force plate.
Ooh.
Yes, this is what the Jedi Knights use to measure the midichlorian levels. All right? You may think that this looks like a bathroom scale. Actually, it pretty much is a bathroom scale. Okay? But it hooks up to the Logger Pro. And what we're going to do is we're going to put it right down here. Okay? And then we're going to run over here, because I forgot to do this before we started filming. And we're going to get a 1 meter stick and a bouncy ball. Almost dropped that. Okay? And what you're going to see is you're going to see this taped up to here, like this. Now the force plate is just like your force probe, with one exception. We can't calibrate it. All right? Well, we can do a sanity check. We can 0 it, and we have to. So what we're going to do is we're going to start off by somebody in your group should step on it. At you 0. Why me? You 0 the force plate, and then you step on it. And you look on the screen, and it'll tell you how much you weigh in newtons. That should be fun. Didn't you always want to know how much you weighed in newtons? Then, after you get off it, another one of your lab group can do it. And when you're all ready, making fun of each other and how much you weigh in newtons, what you do is you have somebody has to volunteer to drop the ball. So you put the ball here, and you go like that. And you catch it. Okay, now, this is important. Okay? You're going to get your signal off of the Logger Pro. You only do it at this station here. And it's going to look like this. Where that should be 0. Now the question is, when you're taking the area, using the integrate function, which is calculus based by the way, which do you use? Do you take the area of this section right here, or all of that? What do you think, Elena?
Just the top?
Just this much? You want to try again?
All of it?
You want to try again?
Only the...
Actually, it doesn't matter. Either one, they should come out the same. Because as it turns out, these cancel out. I didn't do a real great job of drawing. So the area of this, the net area of that should be 0. But usually we just take this area right here. Makes things easier. So you take the area of that. Now, what you're trying to figure out in this part is the mass of the ball. Yes, you do weigh it on a scale. That's easy. But we know that m delta v is going to be equal to f delta t. Now, where do we get these things? Well, first of all, we know f delta t, that's going to be this area right here we just talked about. So you use Logger Pro to get it. How do you get delta v? Well, we know it fell 1 meter. All right? By the way, Elena, your finger is getting close to the lens of the camera and it might show up. Yeah, that's it. Okay, that was Elena's finger. Okay, so we know this number here. If we can figure out this number, we can figure out the mass. How do we figure out delta V? Well, delta V, we're assuming that this is an elastic collision. The ball fell exactly 1 meter. Okay, so we can use this formula right here. Vf squared minus V0 squared is equal to 2AH. Okay, we're just interested in the impact, the velocity, just before it hits the force plate. We know that the velocity, it's going to be the h, how far it falls, is 1 meter. We know the acceleration is due to gravity, so that's going to be g. And we know that the initial velocity when it rolls off the ball, off the top of the ruler, is 0. So we end up with Vf squared is equal to 2g. We can solve that, and we get that it's the square root of 2g. Easy. All right, but we don't want Vf, we want delta V. And that's where the part where this is an elastic, we're assuming that this is an elastic collision comes in. Because what we're assuming is, we know that the velocity is going to be the square root of 2g going down when it hits. But then the velocity is going to switch and going to go, as an elastic collision, the velocity will stay the same in magnitude, but the direction will be the opposite. So then the velocity now is going to be, delta V is going to be equal to what? What's delta V going to be equal to? Now, this is the question that I always ask everybody. I'm asking you right now. You, yes you, not your lab partner, I'm asking you. What is the delta V? And almost everybody gives the same answer. And they say it's 0 because the velocity is the same going down as it's going up. It's not. The magnitude is the same, but the direction is the opposite. It's like if you run into a wall and bounce back, and you're running back the other direction. Your velocity didn't stay the same. If you did, you would have run through the wall. All right, but you didn't run through the wall. You bounced off because you're a moron. Why are you running at a wall anyway? That's not a sane thing to do. As it turns out, delta V is going to be equal to 2 times Vf because it's an elastic collision. All right, so it heads back up. Bam. So you know delta V, you know F delta T, you can figure out the mass. All right, so you get a good answer, right? No, you get a lousy answer. Why did you get a lousy answer? Well, let's look at this experiment one more time. Where did there's the ball. All right, if we do this again, if it was an elastic collision, we would see the ball fall. If it came up at the same velocity, it would come up to the same spot, but it doesn't. It only ends up about halfway up. It's not really an elastic collision. All right, maybe I could get a better ball. I don't know. Don't throw it at it. That's not going to help. Okay, that just makes... So, you're going to get something, you're going to be off by 30%, and you're going to ask me, hey, man, is this right? Probably, don't drool, please. I really hate it when people drool on the equipment. It is. You got the right answer. You got the wrong answer. All right? So, that part is probably the one that people have the hardest time understanding. It's the 5th part. Parts 1, 2, 3, and 4 are the part that people spend the longest on because they don't know how to cut thread or tie thread. Part 3 and 4 are really pretty easy. Once you get through parts 1 and 2 and you understand how it works, it's pretty fast. The point is, come early, take lots of data, and get it done so we can all go home. How's that sound?
Good.
All right. Cut.